The next thing we're going to do is show how the Cauchy integral formula and its proof give us an important convergence theorem. We could have done this earlier, but maybe with a little more background in the Cauchy integral formula, this will seem a little easier. But we're going to talk about local uniform convergence here. So let Fn be a sequence of functions. So I have f1, f2, and so on. A sequence of functions on the open set U in the complex plane. And we say Fn goes to f, so f will also be a function on U, locally uniformly, exactly what you might guess. So if for every z naught in U there exists a radius such that Fn converges to f uniformly on that disk. So that would, you could say that as the supremum of the difference on the disk of radius r centered at z naught goes to 0 as n goes to infinity. And now the very important theorem is that if I have a domain and I have a sequence of analytic functions and they converge locally uniformly on that domain, then the limit has to be analytic and the derivatives converge locally uniformly. Okay, an easy corollary of this before we do the proof and some examples is, well, in the same setup of the theorem, we get that for each point in the domain and k greater than or equal to 0, that these power series coefficients, which just come from derivatives, converge to the right power series coefficients. So I've written it this way just so it's clear, because up above we know that if the functions converge locally uniformly, then the derivatives do too. So you can take multiple derivatives, so you also get, the kth derivative will converge to the kth derivative locally uniformly. And then this is just applying this at a single point, but it shows that if I go to the point z naught and compute Fn's power series in terms of powers of z minus z naught to the n, then the coefficients here converge to the coefficients of f. Let's see, let's do a couple examples before we prove it. Let's consider this sum of principal log of 1 over 1 minus z to the n. Here we're going to keep z in the disk, so this always makes sense. And we claim this converges to an analytic function on the disk. Why is that? Well, basically we'll use the Weierstrass m-test and some basic estimates. So for z less than or equal to r less than 1, the absolute value of this principal log, I'm just going to write it in a simple way. So principal log vanishes at 0, so it has a z in front of it, and it's a simple 0. So there'll be this analytic function here, which I don't need to know too much about it, but I can bound this function by r and then by the supremum of g on this disk of radius r centered at 0. And that's useful because, well, these r to the n's are getting smaller, so I can bound this infinite sum of absolute values. Well, I'll get these r terms in front, that's where this r to the n comes from, and this constant here would come from taking the supremum of g for z less than or equal to r to the n, but getting rid of the n just makes the estimate worse, so that's fine. And if r is less than 1, this is a geometric series, which is finite. So I get out of this absolute and uniform convergence on this disk. And so this gives me local uniform convergence because I can do this for any little r less than 1. So for any point in the unit disk, I can, so if here's the unit disk and here's my point, well, I can just go out far enough and I have uniform convergence on this larger disk. So certainly there'll be a disk around it where I have uniform convergence. We can play with this example a little more. It's actually a very important function after you exponentiate it. We can show that this infinite sum here, well, we can write it as this double sum of positive stuff. And we already know that this converges in the disk, namely for z less than 1 in modulus. And so this gives me absolute convergence of this double sum, so I'm allowed to rearrange the sum with the absolute values removed, which would give me the original function I had, where this is just parentheses. And so this double sum converges absolutely in the unit disk, so I can change the order. Then on the inside, I get this geometric series, and so I can convert the original log series into this. Okay, now let's look at another very important example. Let's look at the Riemann zeta function. So here it is, the infinite sum n to the minus z. So e, when we do this, it's a power function technically, and I should technically tell you what branch to use, but these n here are natural numbers, so we're just going to use natural log of n in the definition here. And this converges to an analytic function for real part of z greater than 1. Why is that? Well, I can look at the absolute values of these, and I get n to the minus real part of z. So if I sort of fixed real part of z greater than rho greater than 1, or let's say greater or equal to rho, then I could bound this by a fixed number and get absolute and uniform convergence on a half plane. And so you'd get that this converges to an analytic function on this half plane. So that's the real part of z greater than 1. And the function we have here is usually written as zeta. People call it the Riemann zeta function. Sticklers will call it the Euler zeta function, I think. It's often written with the variable s. For some reason, when you study series like this, you write the complex variable as s equals sigma plus it. So just so you're aware of that. Okay, so these are some really important examples that you get out of knowing that local uniform convergence of analytic functions will give you an analytic function. So let's prove that. So let's prove that theorem. So we'll fix a z0 inside our domain, and we have to have an r such that fn goes to f uniformly on this closed disk. If we didn't have a closed disk, we could shrink in and get a closed disk. And now we're going to apply the Cauchy integral formula on this disk. So fn of z is equal to what we had for the Cauchy integral formula on a circle. So it's an integral over the circle of radius r centered at z0. Now we have uniform convergence on the closure of this disk. So certainly at z, we have pointwise convergence. So the fn of z's converge to f of z. On the other hand, in the integrals, since we have uniform convergence, the integrals converge to the integral. So here I get f inside the integral. And this is just from this estimate here. If you were to compare these two integrals and put absolute values inside, we would need to estimate this thing. And it's not too bad to do that because on this circle of radius r centered at z0, well, w minus z, I can bound that because z will not be on the boundary. So I can bound that by a constant that depends on z. And I can bound this part by the supremum of the difference. And I know that this tends to 0 as n goes to infinity. So I can get that the integral, that the limit of the integrals is the integral of the limits. And now I'm just going to refer people back to our proof. So this isn't maybe a great way to organize things, but in our proof that holomorphic implied analytic, we basically showed that if you had a formula like this, then you could manipulate the 1 over w minus z using power series to show that the function, in fact, has a power series representation. I don't want to go through that all again, but the point was you play around with this function here, and you write it as an infinite sum that you pull outside of the integral, and all you really needed for that was the continuity of f here. We know f is continuous because of uniform convergence on this circle. Okay, and so you get a power series representation for this integral, but that it's also equal to little f here, so you get that f is analytic. So that's the main part. We have local uniform convergence implies that f is analytic. The next part is that the derivatives converge locally uniformly. For that, this would depend on a homework exercise, that the derivative of an analytic function can be computed using a modified Cauchy integral formula where you put a square here instead. And now you can just compare f prime and fn prime using the integrals. So we take z minus z naught less than or equal to s less than r, just to give us a little room to work. And you compare the integrals up above and put absolute values through everything. So on the inside we'll have this part, which we're just going to, the nice thing here is that we can just control this with the supremum of the difference of f and fn, while the bottom, what is that part? Well, that's why it's important that we've kind of moved in a little bit. So we get that w minus z is greater than or equal to w minus z naught minus z naught. So I can bound this by r minus s below, so I get this bound here. And let's see, the 2 pi r came from the radius, and computing the area, the length of the circle, and we're sort of fixing this relationship here. So you get that the supremum of this difference on this disk goes to 0 as n goes to infinity. So that's uniform convergence on this disk of radius s centered at z0. So we had to move in a little bit, but we still do get local uniform convergence of the derivatives, and that proves the theorem.